Morning, everyone. Happy Halloween. My name is Matt DeLaCluse. I'm the General Manager with RAECO Rents. I'd like to thank you all for taking the time out of your busy schedules to join us for Vibration Measurement 101. Our presenter today is Bob Selwyn from Sensidyne. In this 45-minute free webinar, he will cover the following: overview of vibration measurements from the human perspective, hand-arm vibration from tools, whole body vibration from vehicles and machinery, nuisance vibration in buildings, and ask the expert your questions answered. Bob is the sales manager at Sensidyne, specializing in Savantic sound and vibration products. With more than 38 years of experience in industrial hygiene, Bob is an expert in assisting users of personal noise dosimeters, sound level meters, and vibration meters. He helps others understand regulations and how to carry out relevant surveys. Bob graduated from Liverpool University in the UK with a bachelor's degree in applied physics with a major in acoustics in the mid-1970s. Bob has more than 20 years of experience in the European Union and over 15 years here in the US, assisting users around the country make better noise and vibration measurements in the workplace. He has been with Sensidyne supporting the Savantic line for the last 4 years in North America. Because of the large number of attendees, we will be muting the phone lines. If you have a question, there is a question chat tool built in GoToWebinar. Please enter your question and we'll make sure it gets answered. Now I'd like to turn the microphone over to Bob. Welcome.
Welcome, everybody. This is Bob Selwyn from Sensidyne. Good Monday morning. I'm looking forward to talking to you about this subject. We're going to talk about the levels of vibration to begin with, just set things into place, talk about a few terms, and set the scene. And then following on, we're going to look specifically at vibration affecting humans. That typically means looking at vibration that people pick up through their hands, operating power tools. Then we're going to go on to look at vibration that affects people being transmitted through their bodies, whole body vibration measurements, that subject. And then finally we're going to look at the nuisance aspect of vibration affecting various things that we don't want it to. We'll get through this in the allotted time and hopefully have some time for some questions later on. So welcome everyone, and let's get going. Okay. So vibration, I guess we all have pretty much an idea of what we're talking about here. Everything vibrates. This is the cause of all sorts of problems for us. If the vibrations are transmitting through the air, typically we call them sound if we want it, or noise if we don't want it. Vibration travels also through substances, through materials, and we can perceive that as wanted or unwanted. It can be comfortable, uncomfortable, and if it gets too bad, even dangerous. So that kind of sets things going for us. As far as vibration through solid materials, then this is a typical example. Could be work going on the ground, or as we see here, a subway passing close to somebody's house. The vibration comes through and affects a particular building, and we'll see how all of that happens. So it's basically the transmission of energy from a source to a receiver, and again, very similar to sound. Distance plays an effect. We have to consider the speed of transmission, the amplitude of these vibration waves traveling through the solid that we're thinking about. We have the speed of vibration changes, and of course the direction that the vibration travels in. So as far as actually measuring what we're doing here, I mentioned that we have some similarities as far as sound measurements are concerned. As far as the sound and noise measurements are concerned, typically we use a single transducer, the microphone, Microphone is an omnidirectional device. It is responsive to the signal that it receives coming from all and any direction, deliberately designed to be so. So it means that from the sound point of view, a single microphone can pick up everything that we're interested in. However, when we come to think about how we make measurements with vibration sensors, we're looking at an accelerometer. On the right-hand side here, you see a typical accelerometer that's used for measuring vibration. But unfortunately, a vibration sensor, because of its design, is really only sensitive in its main axis through the body of the instrument, usually top to bottom. And so, to be able to gain a complete picture of a vibration issue, we really need more than one sensor, more than one accelerometer. So typically we measure in 3 axes, and that enables us to collect all of the information that we need to correctly gain the overall value of the vibration and, if necessary, know its direction as well. So when we talk about vibration, typically we're talking about an issue which has both a magnitude and a direction. So for our vibration measurements in 3 directions, we use typically an accelerometer with 3 vibration sensors built into it. We call these triaxial accelerometers, 3 axes measuring the vibration in all 3 of the axes. So we measure in an X direction, a Y direction, and a Z direction, and that gives us the ability to make sure that whichever direction the vibration is measuring in, we can capture it correctly. So we're typically looking at the overall vector sum, which we find just simply by finding the square root of the 3 axes, each individually squared. So our true vibration amplitude is the X squared plus, not equals, plus the Y squared, plus the Z squared, summed and then square rooted. That gives us our overall vibration amplitude. So, like most measurement techniques, we have a certain language that we use to characterize the vibrations that we're measuring. So we talk about the peak value. Since these vibrations are caused by something moving, if it's moving in a very simplistic manner, it'll be at rest at one position, it'll move in one direction up to a maximum value, back down through the rest position, it'll vibrate in the other direction and then come back and make a complete cycle. So our maximum excursion we call our peak value. The difference between the positive going and the negative going excursions we call the peak-to-peak value. The RMS value is the energy equivalent value in that time, the average value over a given time interval. We talk also about the period of oscillation, how long does it take for a complete cycle of operation. We're looking at an example here of a 60 Hertz sine wave. So the period of oscillation here is just over 16 thousandths of a second. And the frequency of oscillation, how many cycles per second? Well, 60 Hertz defines 60 oscillations in a single second for us. So this is these are the key parameters that we'll be discussing and that you'll come across doing any vibration measurements. That was a nice simple signal, a nice simplistic sine wave signal, but typically vibration signals are rather more complex than that. This is a typical time history of a bearing measured on the side of a machine. It just happens to show that as the bearing is going around, there is a little nick in one of the ball bearings in the race, and each time that nick is energized, it produces a spike, and we see these spikes being indicated here, the very high spiky peak levels in between the random vibrations that you see for the most part of the signal. So there's quite a lot of information that is available to us to use for our analysis. And again, similarly to making noise measurements, frequency analysis is a popular way of gaining a useful insight. So the two examples that I've got up on the chart here show frequency analyses, first of all on the top in 1/3 octave bands, going from about 1 Hertz up to about 2.5 kilohertz. So we can see the green bars are each of the individual 3rd octave bands. The two red bars at the right-hand side are the sum and the overall values of all of the vibration signal that may be present there. In the lower trace, the information there is a narrowband spectrum, a narrowband frequency analysis measured using a technique called FFT, Fast Fourier Transform Analysis. And this is really useful for identifying tones or specific frequencies and their harmonics in a signal. So you can see here the red trace is a max hold of a signal that was measured shortly before this screen capture was taken. So bearing in mind our frequency analysis, we also have use in collecting time history information. The time history shows us how things are changing. Here we're measuring 3 values here. We're measuring the top line P1 is an acceleration signal, milli-Gs. The second signal is a velocity signal in inches per second, milli-inches per second. The third signal is the displacement, how much the thing was actually moving. So we're looking at mil, 815 millimils. And the trace on the bottom of the chart there gives us a good indication of the time history and how things are changing during a cyclic operation. Okay. So typically we would talk about the vibration signals being in meters per second squared, an acceleration, and velocity in meters per second, displacement in meters, millimeters, micrometers. But sometimes when we make measurements, it's also useful to be able to relate these in decibel terms, take logarithms, as we do for noise, except we obviously have a different zero value, a different reference value. So if we're talking about acceleration decibels, we use the value of 10 to the minus 6 meters per second squared as our reference point, as our 0 dB acceleration point. So a 1 meter per second squared acceleration, we would describe it as being 120 dB. A velocity measurement, the reference there is 10 to the minus 9 meters per second. So 1 millimeter per second is 120 dB velocity measurement. And displacement, here we use 10 to the minus 12 meters as our reference point. So simply a displacement of 1 micrometer also happens to be 120 dB. So you can see for a start, because we're measuring 3 different units, it is important to distinguish between them. So we talk about dBs of acceleration, dBs of velocity, or dBs of displacement. Okay, so having reviewed perhaps some of the main terms that we'll come across later on during this, let's go on to look at how vibration particularly affects people. So we're specifically looking primarily here at the hazards of vibration in the workplace, where people work, where they're subjected to machinery or things that are vibrating in such a way as a problem for people. So the primary one that we're going to look at, or the first one that we're going to look at, is vibration affecting the hands and arms. Then we'll take a look at vibration affecting the whole body of a worker, of an individual, and we'll finish off then looking at the effect of nuisance vibration, which is typically something that we worry about as far as machinery at work and spoiling things that our delicate machinery is trying to perform for us. So let's take a look at each one of those in a little bit more detail. So for hand arm type vibration sources, we find pretty obviously there are a lot of people around that use vibration or vibrating tools. They hold them with their hands to control them. You see a couple of examples here, a grinding tool on a metal pipe, and a gentleman who hopefully is wearing not only his steel-tipped toe cap boots, but hopefully also has his hearing protection and possibly even some anti-vibration gloves on. But he's going to be using this road braking tool to break up the tarmac. It produces quite high levels of vibration that's transmitted through his hands and arms. Other sources we have polishing or grinding, and of course forestry workers using chainsaws. It's quite surprising how much energy there is in a chainsaw when it's cutting. It can be producing some strong vibrations that transmit into the worker's hands. Anybody else that we can think of that might be affected? Well, landscape gardeners, shouldn't overlook them, but holding on to any form of grass cutting or hedge trimming type of tools, these have a motor inside them to drive a cutting device, and that motor, particularly as it's cutting, can produce some substantial hand-arm vibrations levels as well. Polishers, an automotive industry here, somebody using a hand polishing tool is another example. Dentists also using drills, teeth cleaning tools, surprising, but they also have been found to suffer some forms of hand-arm vibration issues. Even tattoo artists using small drills, they use the drills to paint pretty pictures on people's skin, and that's an impulsive source. It also produces vibration levels that can, over a period of time, give them difficulties as well. So here's some common sources that we can think of straight away. A list here shows the various industries that have been sorted into hand-arm potential problems, and you can see the common sources of vibration. So diamond cutting, we're looking at vibrating hand tools. The forestry industry that we saw before, chainsaws cutting up the trees and the logs and stuff. Furniture manufacturing, pneumatic chisels. In the mining industry, of course, people use rock drills to break up the rock to be crushed. All of these things, even down to stone dressing and making those sorts of things, they're used to chip away and to etch and carve out the words and messages on gravestones and things. So all of these are examples of common sources of hand-arm vibration that we may come across. How big a problem is it? How many workers are affected? So here's a list that was published by NIOSH. Shows the main industries and number of workers here. So in the construction industry, they reckon probably about 500,000 workers using some sort of hand tool that could be a problem. Farming industry also, chainsaws and other tools, 200,000 of those. Metal workers, steel workers, lumber and wood, furniture manufacturing. You can see the numbers here. All this lot adds up to typically about 1.25 million US workers at risk of hand-arm vibration issues if they're working in these industries using these types of vibrating sources. Now, what does this look like as a problem? Well, we know, for example, people suffering from noise at work start to go deaf. People suffering from vibration from hand tools start to feel tingling in their fingertips. The ends of the fingers start to change color. You see this whitening of the ends of the fingers. The symptoms here go from white finger, vibration white finger as a disease, to this picture below where it really gets to be nasty. The worker has difficulty holding small objects, The nerves have been damaged, the blood vessels have been damaged. Once the blood vessels are damaged and the blood no longer can go to the fingers, in its worst case, you can have potentially gangrene building up, and ultimately a worker may need a thumb or finger or fingers even to be amputated. Not a pretty sight. Again, some more examples here that you'll find. These are all early onset signs here, but the picture in the top right-hand corner there certainly shows a couple of fingers that are starting to get this white finger syndrome. So is this something that happens the first time you use a tool? Well, no, luckily. Again, you're not typically going to go deaf from one loud exposure to noise. This is something that gradually builds up on people. So there's a term called latency, which is the time taken for the onset of the various stages of vibration white finger. Problem with the hands. So we start off with a tingling. Foundry worker may take up to a couple of years to start to experience tingling in their fingers. Numbness, again, over a couple of years, maybe 2.5 years and upwards. And then the whitening, again, is sort of approximately a 2-year interval for that. So it doesn't take long for a foundry worker to be working regularly with these things. And this is not doing it 8 hours a day. This is a typical work shift where they have on and off periods. But after these sorts of lengths of time, this is typically when these problems start to arise and be visible and obvious. So we can just look through this list. Chainsaw operators in the forestry industry takes a little bit longer, maybe 4 years there, but still you see these are not too long. So what's the scale of the problem where people do suffer this? Well, I did some examples from England about 10-20 years ago. Back in the late 1990s, the High Court in the UK awarded this figure, almost $200,000, to 7 coal miners who were suffering from vibration white finger, almost $28,000 dollars each for each individual claim. And once they had done this in '97, the UK government set up a fund to cover the claims by other ex-coal miners, such that after 6 or 7 years, by 2004, they actually paid out over $160 million in compensation. So there have been a number of successful claims for compensation for this hand-arm vibration syndrome. It is something that people do make claims about. It is a problem that they want compensation for. So how can we estimate the risk? How can we know whether it's a problem or not? So there's a number of ways of doing this. We can use the manufacturer's stated vibration values to sell a product that potentially may cause hand-arm vibration. The manufacturer has to make a statement about the expected levels of vibration. However, it is a fact that in studies different people hold the tools in a different way, and there can be some significant differences, 10-12% between users even of the same tool. Also, the age of the tool and condition of the tool obviously is something which causes different readings, different exposures to be experienced. And when a manufacturer makes a test measurement of something like a chainsaw, they're going to do it under standard conditions. The standard conditions are typically with no loading. It's not cutting anything, it's just vibrating, and the user is holding it. So we have these small devices, relatively low-cost devices called tool timers. And the tool timer is basically a little switch that you attach to the tool that just measures how long each individual exposure duration lasts. And the idea there is with these tool timers, this little device is sensitive to vibration. It just clocks up the time that the tool is in operation, and then you look at the manufacturer's information and you multiply the duration by the original exposure, and that is supposed to give an estimate of the day's exposure for an individual. Unfortunately, it's prone to some quite large errors, and it can have some very wide tolerances. It's not a particularly accurate or recommended method, but it is at least a first step. Okay, so just like we have proper standards for the instruments, we don't want to just use any old instrument. We need to have something which complies with at least a recognized standard. So ISO 8041 is the instrumentation standard for measuring the human response to vibration. ISO 5349 parts 1 and 2 are the measurement standard telling us how to use these instruments. And the last standard here, 15230, is talking about the coupling forces, how the user actually holds the tool, the way that the measurements should be made on the tool to make sure that the forces that the tool is producing are being undertaken. So these are the relevant standards that you should be looking for in any equipment that you use and any methodology that you use. These are good standards for gaining that information. So how do we measure the hand-arm vibration? Well, we really need to measure at the point of contact, hand and the tool. So our 3 directions are based on the hand gripping the handle of the tool or on the tool itself. If possible, obviously people have 2 hands and more often than not hold the tool with 2 hands. So bear in mind, if you choose one over the other, you may not necessarily be measuring the worst case. Even with a single tool, it can be very useful sometimes to make 2-handed measurements, for which you need an instrument that has 6 channels, because we're measuring 2 times in the X, Y and Z directions. It's also a good idea to measure for the whole time that the tool is used. That way you're not missing any of the potential exposure, and you are able to get a representative period so that you can use that later on if you know how long the worker is going to use a tool for. So the last of the ISO standards a couple of slides ago that I mentioned, 15230, talks about the coupling between the hand and the handle and suggests that the best place to actually measure the true vibration that is being passed into the hand is to have the sensor between the palm of the hand and the handle. So we need to think of something small enough that the operator can actually still grip the handle of the tool and be measured at the point of contact. So we can also mount in alternative places. We can mount accelerometers on the handle itself, perhaps in addition to in the palm of the hand. That way it's possible to measure what the tool is doing and what the worker is receiving, and to see the effect of perhaps any design that the manufacturer has made on the handle to try and reduce the vibrations. Just bear in mind that measuring on the handle of the tool will give you a reading. If you think about it, if the tool is on and working and vibrating and you have the accelerometer as shown on the top picture here, if the worker lets go of the handle, the accelerometer is still going to measure exactly the same vibration as it was when the worker is holding onto the tool properly. So in all cases, pretty much the most important place to measure is in the palm. These are other alternative measurement positions that can perhaps aid the manufacturer of these tools to try and reduce the vibration in some engineering way. Okay, so what do we measure then? We talked about some of the units, our peaks and RMSs and that sort of thing, but are all frequencies of vibration equally important? Well, research over the years has shown that there is a range of frequencies that we really ought to be concentrating on, and this is shown in the chart here. This is a shape of the frequency filter that's built into these vibration meters that's a little bit like the A weighting filter in a noise dosimeter or a sound level meter that passes certain frequencies and attenuates the lowest and the highest frequencies. We have the same thing here. We call this the WH filter, H for hand measurements. It basically covers the range from 1 to about 1250 Hertz, but it has its main sensitivity in the range from about 8 to 16 Hertz. So you'll see the curve here on the chart. This shows what the instrument is going to do to the various frequencies that come in to give us our overall frequency filter weighted vibration measurement. Okay, so how can we deal with this? Well, this is a typical example of a measuring tool, an instrument which has two inputs. It's a 6-channel instrument, so potentially we could connect 2 of the hand vibration sensors to it and measure both left and right hands simultaneously. We can set the instrument up appropriately to measure what we want. We measure for a representative period of time. If a worker is going to use a number of different tools, then we really need to collect exposure information about each of the tools separately so that we can include all partial exposures from the different sources over the different durations. We can also deal with it with a smaller device, so you can think perhaps of that previous instrument as being the equivalent of a handheld sound level meter. Somebody is there to operate it and to make the measurement, but just like we have noise dosimeters that a worker can wear without the need for any supervision, this is an example of a vibration dosimeter specifically aimed at hand arm measurements. The worker puts the hand strap on a short length of cable and the small body of the accelerometer fixes to a strap on their arm. They can be completely autonomous. They don't need anyone to walk around with them. This is a very easy way to collect information. The unit is so small it can actually be worn all day, so you can fit somebody up with this at the beginning of their shift excuse me, and leave it on them for the whole of the day, and it will include everything that they are subjected to. Okay, so we've seen what we're going to measure, we've seen how we're going to frequency weight it, we've seen some of the examples of the instrument. So are there any limits? What are the limits that we're trying to stick to? So around the world there are various limits, but particularly in the European Union, they talk about 2 values. They talk about an exposure limit value, an ELV, which is a calculated 8-hour average vector sum of less than 5 meters per second squared. The second value that we talk about is the exposure action value, and that's a lower level. That's a level of 2.5 meters per second squared. So this is a little bit like the action level in the noise work that we do and the permitted exposure level that we have as the limit for our noise exposures in the workplace. So there is also, again, very similarly to noise work, there is this concept of vibration dose. So we talk about the 2.5 meter per second daily action level as being equivalent of 100% dose, and we can measure in exposure points. A point is a 1% dose value. So somebody that receives over a working day 50 points, we would know that they only had a 50% dose level. That would be under the 2.5 meters per second squared action level. Very similar to a noise dose concept. So in the US, there is an ANSI standard, ANSI S 2.70, and this also talks about an action level and a limit level. We have a daily exposure action value, DEAV, and a DELV, and again here in the ANSI document it's 2.5 meters per second and 5 meters per second. This is again the average value for a full 8-hour workday. So again, there can be periods when the exposure may be higher, but there have to be certain off non-exposure periods so that the average works out to less than these. This is just plotting those values as a response curve, exposure time along the bottom axis and the level of acceleration that we measure on the vertical axis, and you'll see the various zones indicated there that are the risk zone and the health risk, high health risk zone. ACGIH also has issued threshold values for hand-arm vibration. It suggests that we should be looking at less than 4 meters per second squared for an exposure between 4 and 8 hours a day, less than 6 meters per second squared for 2 to 4 hours in the day, less than 8 for 1 to 2, less than 12 for an under 1 hour exposure. So again, the concept is as the level of vibration goes up, the exposure time should be reducing to try and minimize the average exposure over the working day. Slight difference here, the ACGIH recommendations actually talk about the average level, the equivalent acceleration level, AEQ, in meters per second squared, but they talk about a dominant axis. So rather than being the resultant of the 3 axes, as we saw before, this is for any one of the 3 axes, either the X or the Y or the Z axes should be less than these limiting values. So what do we measure if we do these sorts of things? What values do we see? Well, we see the tools down the left-hand side. We see some typical acceleration values for a good condition tool, a typical condition tool, and a tool in very poor condition, one that hasn't been looked after. And you can see the recommended maximum exposure times here. So let's just choose something, table here. Impact wrench, a typically looked after impact wrench shows us that that's going to produce somewhere around 4 meters per second squared. So a worker would be up to their maximum exposure time in just 3 hours using that particular tool if it wasn't really looked after very well. So we have to calibrate the instrument. So we see some calibration devices here. They have to work over the appropriate range. They produce a steady level, and we mount the accelerometer onto some sort of adapter that fits on the shaker of the calibrator. We produce a steady vibration and make sure that the instrument is checked by reading in each of the 3 directions the value that the calibrator produces. So calibration is important. It just takes 3 times as long as with a sound meter because we have to calibrate the 3 axes. So some solutions for hand-arm vibration then. Keeping hands warm is always good to maintain good circulation. Keeping the tool handles warm in cold weather use is also a benefit. If they're cutting tools, then changing the blade or changing the cutting tool itself, making sure to keep that sharp is certainly a good practice. Many manufacturers offer low vibration tools, and wherever possible it's always a good idea to choose those. Maintaining the tools properly, anti-vibration gloves as personal protective equipment. Not smoking. Smoking is another cause potentially of reduced blood flow, so let's not make it any worse than it's going to be. And of course, moving people between jobs to minimize their individual exposure. Somebody may only need to be exposed during the morning, and then at lunchtime or halfway through their shift they can go over to a different job and somebody else can take over using that tool in order to minimize the individual's risk. So these are some examples of people using these tools, drilling, running tools onto stuff in production. This is a typical example of how things might be exposed and the measurements that can be made. And then, of course, when you download the results to the PC, you see the time history. This is a typical example of somebody using a drill, making 3 drilling operations, and you see the higher levels for those 10-15 seconds when the drilling is taking place and the signal dropping off in between. So it's the combination of both the on and the off times that we want to consider. Okay, so we've talked about hand-arm. Let's go on to the whole body vibration. So here we're talking about people that sit in these sorts of off-road vehicles, truck drivers, train drivers, earth-moving equipment, helicopter pilots. These can also be very very shaky jobs where the operators are sitting in a machine that is shaking them around a lot. Farmers on tractors, concrete crushers, road breakers, these sorts of things. Here we go, here's some other examples. And when we're talking about whole body vibration, we're basically talking about the vibration that's transmitted through the seat for somebody sitting on a vibrating seat, or through the feet for somebody that's standing on a surface that's being shaken. We're looking at the large shocks and jolts that cause people lower back pain. In terms of the number of workers at risk here, this is almost 7 million, more actually than the hand-arm vibration measurements that we were looking at before. This can certainly affect people. Unfortunately, this is something that isn't quite as visible as hand-arm vibration. You don't see blood coming out of somebody's back. You don't see their back changing color like we did with the hand-arm vibration. But for those people who suffer from it, it can be really nasty. So here's an example of a claim and an award. 2011, in February, Texas court awarded a train driver almost $2 million for a spinal degenerative disc injury following a trial working on the railway line. So these things do happen, and juries do award money to workers that suffer from these problems. How do we deal with it? Well, we have our individual, we have our 3 directions, the X direction front to back, the Y direction side to side, and the Z direction from feet or backside up through the head. Again, we need to measure all 3 axes. If somebody's sitting on a seat, they're going to be shaken around all over the place. So our sensor for this is one of these discs. It's about 9 or 10 inches in diameter. It's about ½ an inch thick, and basically you either stand on it or you sit on it, and it measures what you're receiving through the seat. We have to measure for at least 20 minutes to get a representative sample. We have some frequency correction curves. Again, some of the frequencies are more important than others. About a lower range of frequencies, so we're talking down to ½ a hertz up to about 80 hertz for our overall range, with a specific sensitivity from about ½ to 2 hertz. We have a filter whose shape looks like this, called the WD filter, that's used for the X and Y directions, so that's the horizontal directions effectively, and we measure this unit, the A8, the average level for an 8-hour, and possibly a new unit which I haven't mentioned yet called VDV. Okay, for the Z direction, the Z direction, let's not forget about that one, but because of the different structure of our bodies, we have a different frequency filter shape for this one. Still again, ½ a hertz to 80 hertz, but this time 4 hertz to 12 hertz are our main frequencies of sensitivity. So we measure with a filter called the WK filter. Again, we want the 8-hour average and possibly this VDV value. Frequency measurements are important here in whole body measurements, and the ACGIH TLV limits specify the different frequencies in 3rd octave bands that we take with an instrument and then plot against these time exposure curves. This is the X and Y axis set of exposure curves. This is the Z-axis set of exposure curves with the different frequency sensitivities that we saw before. So we measure with the seat pad, as we said. We take our readings for our X, Y, and Z axes, except instead of measuring them by just squaring and taking the square root, we have to measure the X and the Y axes by a factor 1.4 to represent the fact that they are actually considered to be the more dangerous of the 3 axes, because they involve twisting of the spine rather than just the up and down movement of the spine. So I've mentioned already a couple of times the vibration dose value, this VDV. So what is the VDV? Well, it's a measurement, it's a dose value, and it's a dose value that is used if the vibration that we're measuring is particularly peaky or impulsive in nature. You think about somebody in an off-road vehicle driving down a haul road in a forest, that may be okay, but as soon as he goes off ground and over the rocks, there can be quite a lot of shock and impulses being transmitted. So we measure this vibration dose value in a slightly different way, and we come up with a unit which has units of, we come up with a parameter that has units of meters per second to the power 1.75. Don't worry about these, the instrumentation takes care of all of this calculation and measurement for you. You just have to know that if there is a lot of impulsiveness in the signal, then the VDV value is going to be an important value to consider. So how do we know if it's peaky enough? Well, we use this measurement of the crest factor of the vibration, the ratio of the peak value to the RMS value. Going back to the chart that we saw right at the beginning here, the peak value is the highest value, the RMS is the measurement of the energy in the signal. If that ratio is greater than 6, that's basically telling us it's an impulsive source. We should be using the vibration dose value. So there are a couple of whole body vibration limits. For the regular vibration, where we use the A8 average value, we're looking at an explosion action value of only half meters per second squared, 1.15 for the exposure limit value. And then the equivalent limit values for the vibration dose value for the VDV are an action value of 9.1 and a limit value of 21. Some typical values here. Let's think about something. Let's look down the list here again. A particular vehicle, the ATV, about halfway down, four-wheel drive, off-road type vehicle, can produce an acceleration level here of up to 1.2 meters per second squared, even as an averagely maintained exposure. So that's only going to take 1.5 hours to get to the exposure action value, and 7.5 hours to get to the limit value. That's almost at the point where anything above that is going to be a problem for us. Again, we calibrate the equipment with a calibrator that has a suitable level and frequency range. Bear in mind that for whole body vibration instrumentation, just go back to the chart that we saw a few slides ago, it is an even lower range than the hand-arm vibration. So the standard tells us that we have to calibrate a whole body sensor actually at 16 Hertz. So there are not as many vibration calibrators that can produce a signal at 16 Hertz, such a low frequency. This is an example of such a calibrator here. And just like we did before, we attach the sensor in each of the 3 directions to an adapter that we can screw to the shaker and shake it at 1 meter per second squared at 16 Hertz in each of the 3 directions to perform our field check to make sure that everything is okay with our measurement equipment. So our solutions for whole body vibration, we can think about producing or purchasing, newer, lower vibrating technology. The manufacturers all the time are trying to reduce the vibration that their equipment produces. They have vibration dampeners on the vehicles to try and cut this down. They have suspension on the seats. Sometimes it works, sometimes it doesn't. You have to obviously maintain the equipment properly. Scraping the road surfaces to iron out bumps and lumps and things, and then redoing a whole road is a good way of reducing the vibration, filling in the potholes on the rough road. Sometimes there are some tools that an individual doesn't have to, or some vehicles, that an individual doesn't have to actually sit on or stand on to operate. They can have remote controls, a cable and a handset potentially, and air seat suspension to vehicles as well is a good way of reducing the impact. We can rotate the jobs between individuals to reduce any one single person's exposure time, and we can remove an individual completely by thinking about other ways of doing things. So as far as Human vibration in the workplace is concerned, just a quick review, almost 8 million workers in the US are exposed to whole body and hand-arm vibration. Whole body vibration is the bigger issue compared to hand-arm. That's not to say that either of them is any less than the other. They're both important. They both have serious risks to health and enjoyment of life. There are regulations around the world in many industrialized and developed countries to limit these risks. We need to do regular monitoring to assess what the likely risk is to any workers that we think may be exposed to such vibrations. And appropriate monitoring instruments and methods do exist to make these measurements properly, to make compliant measurements. Okay, I'm just going to finish off now with the last issue that I wanted to cover, and that's nuisance vibration. So we're not talking about a risk to anyone's health here, but we're talking about the nuisance vibration that typically comes through the ground or through the walls or floors of a building, maybe something happening outside or even inside a building that is getting through to the wrong place at the wrong time and affecting delicate machinery, X-ray machines, MRI machines, microbalances, photo etching, all these types of processes that may be going on where the person running this machine needs to have things still and stationary to collect a good in-focus X-ray. Nobody wants to go to the doctor and for him to hold up an X-ray and it looks all blurry and he can't see what's going on. So again, we have potential solutions. The vibration level meter that we saw before, instead of accepting the hand arm or the whole body accelerometers, can accept a more sensitive accelerometer like the one that we see here on this mounting plate that we place on the floor. And we measure in our 3 directions. We find our vector sum and we compare with limits that may have been provided for these different activities that we were talking about in the previous slide. You'll find if you do any of this, you'll find that there are a set of curves called vibration criteria curves, and we plot results on these vibration criteria curves to tell us whether or not a measured vibration that we're picking up on a floor or a wall is acceptable for whatever is going on in that room. So here we're typically looking at an average level plus a peak particle velocity, a PPV. So over a period of time, that is the highest value, not of the acceleration signal, but of the velocity. So we need to be able to calculate both acceleration for comparison with the VC curves, but we also need the peak particle velocity. Dominant frequency is also a problem, so often we need to measure in at least 3rd octave bands, but more usually we perform FFT analysis to identify a particular dominant frequency. Typically, again, it's up to about 80 or 100 hertz, our range of interest here, and certainly down to 1 hertz and even below that. Time history, again, is very useful if there is work going on outside a hospital to do with perhaps road widening or expanding a subway or building a bridge or putting in piling. It's very useful using the time history to be able to show to the person causing the problem that when they're doing certain things, this is when the readings are too high and a solution needs to be found. So for doing these measurements, typically we need a kit that can be both used indoors and out of doors. It's not unusual for consultants to make these measurements over a full day's operation or even longer. So we do need a certain degree of weatherproofing for the equipment. These are those vibration curves that I was talking about. The different values, they're called VCA, VCB, VCC, D and E, and these are the levels represented by the straight line that you see on the little chart there. So they can allow a little bit more vibration level below that cutoff point at 8 hertz, but from 8 to about 80 hertz, the third octave RMS acceleration level must be less than these A, B, C, D or E curves to prevent any problems with the sensitive electronic equipment. Okay, that just about finishes off what I had to say. We've come to the end. I thank you for your attention. I hope it was useful. Just as a review, we've looked at the basics of vibration, some of the terminology. We've looked specifically at the hand-arm vibration as an issue. We've looked at whole body as an issue. And we finished off by considering the nuisance aspect of ground or building vibration. So thank you everyone for your attention. Back over to you, Matt.
All right, Bob, thank you very much for your presentation. Let me see, I'm going to show my screen. All right. I think my screen is up now. If you have any specific application questions, feel free to give us a call. Either myself, 866-RENT-EHS, which is 866-736-8347, or you can reach Bob at his email there. Also, you can reach me at matt@raecorents.com. If you want to know more about the technologies we supply, please follow us on social media. Put out lots of good technical tips on my blog at raecorents.com. You can follow us on LinkedIn and Twitter. And we do record these training sessions, so the recording and the slides will be up on our website and on YouTube. If there are some topics you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists. Please let me know what we should cover at matt@raecorents.com. Our next webinar will be presented by Yemi Muftau-Ladiju on remote monitoring, December 12th, again at 9 a.m. And then we have a couple questions. I think I answered two of them, though, which would be whether the slides would be available. Yes, the slides and the video, a recording of this will be available. Also, someone's asking about the source for the vibration range charts. So I guess Bob might have that to go with the slides, so we'll see if we can get that pulled together. I don't see any other questions at this point, so this will be the end of the presentation. Thank you very much for joining us, and have a great Halloween. Thanks.